Hey there and welcome. Have you ever looked at a chemical formula and wondered, how on earth did anyone figure that out? Well, today we're going to pull back the curtain and do it ourselves. We're heading on a chemical quest to find the true recipe for a simple white powder, magnesium oxide.
So how do we actually do this? You can think of us as chemical detectives. Our clues aren't fingerprints or anything like that. Nope, they're super precise measurements of mass. And our main interrogation tool, a really, really hot flame. We're going to use fire, air, and some careful observation to uncover the hidden identity of this stuff. So here's our game plan. We'll start by understanding our mission. Then we'll lay out the plan for our fiery experiment. After that, we'll get into the nitty-gritty, the techniques that make or break your results. Then comes the math part, crunching the numbers. And finally, we'll talk about what we can learn even when things don't go perfectly.
All right, let's kick off our quest. Before we light anything on fire, and I know that's the fun part, we need to be absolutely crystal clear on what it is we're trying to find.
Our goal, our treasure at the end of this quest, is something called the empirical formula. Just think of it as the most basic, stripped-down recipe for a chemical. It doesn't tell you the total number of atoms in a giant molecule, it just tells you the simplest ratio. So for magnesium oxide, is it one magnesium atom for every one oxygen atom? Or maybe two for every one? That's the mystery we're here to solve.
Okay, mission understood. We're looking for that simplest ratio. Now, let's get to our plan of attack. It's an experiment that's all about fire and air. Now, here's the first big twist, the thing that might feel a little weird. Usually, when you burn something, like a log in a fireplace, you're left with a little pile of ash that's way lighter than the original log, right? But with this, when we burn this shiny magnesium ribbon, the white powder we're left with is actually heavier than the metal we started with. So how is that even possible? It's because the magnesium isn't just burning away, it's actively reaching out and grabbing invisible oxygen right out of the air. And that oxygen has mass. This weight gain is our first huge clue. Getting that result, and getting it accurately, is about more than just following a list of instructions. Success in the lab, it really comes down to good technique. It's kind of like the art of a good experiment. And that art begins way before we even think about lighting a flame. First, we clean the magnesium ribbon with sandpaper. Why? To make sure we're reacting pure magnesium, not some layer of gunk on the outside. Then, we coil it up tightly so it fits nicely in our container and burns efficiently. And of course, we have to weigh everything with extreme precision. These starting numbers are the bedrock for our entire calculation. And now, the main event. We get that crucible glowing red hot, but here comes the most critical move of the whole experiment. We have to lift the lid, but just for a second at a time. It is a super delicate balancing act. We have to let enough oxygen in for the magnesium to react, but we can't let what we're creating escape. This instruction right here is the heart of the challenge. You see that white stuff that looks like smoke? That's not smoke. That is the magnesium oxide we're trying to measure. Every little puff that gets out is literally a piece of our final data floating away. If too much escapes, it can completely ruin our results. Now, even when you think the reaction's over, there's one last pro-level check. It's called heating to constant mass. We heat it up, let it cool down, and weigh it. Then we do it again, and maybe again. When the mass finally stops changing between weighings, that's when we know. That's our proof that every last bit of magnesium has reacted. Okay, the lab work is done. The crucible has cooled down. Now it's time to take our raw data and turn it into a real chemical formula. It's time to crunch the numbers. And believe it or not, everything we need to solve this whole puzzle comes from just these three simple measurements. That's it. The mass of the empty container, the mass with our magnesium in it, and the final mass with our magnesium oxide product. All the answers we need are hiding inside these three numbers.
So here's our three-step roadmap to get from those numbers to our final formula. First, we'll figure out the exact mass of the magnesium and the oxygen that actually reacted. Second, and this is the big chemical secret sauce, we're going to convert those masses into a unit called moles. It's just how chemists count atoms. And finally, we'll use those mole counts to find the simplest whole number ratio.
Step 1 is honestly just simple subtraction. To get the mass of the magnesium we started with, we just subtract the mass of the empty crucible. And to find the mass of the oxygen that jumped in from the air, well, that's just the final mass of our product minus the mass of the magnesium we started with. See, easy. Okay, now for the most important idea here, the mole. Let me put it this way. Comparing the mass of magnesium to the mass of oxygen is like comparing the weight of a bag of bowling balls to a bag of tennis balls. The weight alone doesn't tell you how many of each ball you have, right? The mole is our tool for counting the atoms, no matter how heavy they are. All we do is divide the mass of each element by its special atomic mass. That's 24 for magnesium and 16 for oxygen, and just like that, we know how many atoms of each we're dealing with.
And this is where it all comes together. We lay it out in a nice, simple table. We calculate the moles for magnesium, we calculate the moles for oxygen, then for the grand finale, to find that simple ratio, we just take both of those mole numbers and divide them by whichever one is smaller. And if we did everything right, the numbers that pop out should be incredibly close to a perfect 1-to-1 ratio.
But what if your ratio isn't a perfect 1-to-1? What if it's 1 to 0.8 or 1 to 1.2? Does that mean the experiment was a failure? No way. Absolutely not. This brings us to our last section, when experiments go wrong. This is all about learning to read the story that your results are trying to tell you. Now, in a perfect world, the accepted textbook composition of magnesium oxide is 60% magnesium and 40% oxygen by mass. You can think of this as our bullseye. This is the target we're aiming for, and any little deviation from this tells us something very specific happened during our experiment. And this is how you read that story. Let's say your final percentage of oxygen comes out too low. What's the story there? Well, it means your final product probably weighed less than it should have. And why would that happen? Because some of that white oxide smoke escaped. On the flip side, what if your oxygen percentage is too high? That means the final product was too heavy, which tells you that some of the original magnesium probably didn't finish reacting. See? The mistake isn't a failure. Its story is written right there in the math. So in the end, an experimental result is never just a number on a page. It's evidence. It's a little narrative of exactly what went down inside that hot crucible. Whether your result is spot-on perfect or a little bit off, it has a story to tell. And the real skill of a scientist is learning how to listen to it. So, what story is your data telling you?